topic, maybe let me say something about practical things. The talk is we have allocated a long talk and a short talk. The long one is 30 minutes, including questions, so you should prepare your talk for about 25 minutes, and give some time for questions. And the short talk is 15 minutes, including questions. Okay, so we have some reference prepared. In case you don't like the reference in your guest house, you are very welcome to come here this morning. So I think I don't waste more time. Let's give the first one is Gary Shiu. He changed his topic to collegiality and swampland.
So thank you for having me here. It's a pleasure and an honor to open this year's East Asian Joint Workshop on Fields and Strings. Originally, I plan to tell you about some work that we have been doing on string theory and data science that I'm equally excited about. However, I feel that there probably isn't enough time to give you backgrounds on concepts such as persistent homology and genetic algorithms. So instead, it may be more fitting to talk about the swampland. So this is what I plan to do, to tell you a bit about what's going on with this research program on the swampland. Now, what gave string theory its original appeal is not only that it provides a consistent framework for quantum field theory and gravity to meet, but also a sense of uniqueness. In 10 dimensions, there are only 4 chiral theories that are free of gauge and gravitational anomalies. 2 of them can be realized by the heterotic string, and 2 of them have always been somewhat peculiar, and I will have more to say about that later. Now, moving on to 4 dimensions, the vacuum solutions of string theory appeared to be equally restrictive. There were only a handful of collegial spaces only in the 80s, so few that we can even name them. Now, fast forward 30 years, string theorists have gotten a lot further in finding new ways to construct consistent chiral theories coupled to gravity. In addition to the heterotic string, we can now construct phenomenologically interesting models in every known formulations of string theory. In some corners of string theory, the number of vacuum was estimated to be 10 to the 500. And if you haven't been watching the string theory stocks lately, this number has gone up. And there's no indication that it would stop growing. Now, I put back here in quotes because they are not necessarily local minimum of the potential, as in the case of the electroweak vacuum. However, even so, string theory seems to already give us a huge number of possibilities. This is, of course, the reason why string theory has been a constant source of ideas for physics beyond the standard model. However, this may give you the impression that anything goes. So this begs the question, are there low energy effective field theories that are not UV completable when you couple the theory to gravity? And if the answer is no, we may simply forget about string theory and work directly with these EFTs, knowing whatever we do would turn out to be okay. This is where the idea of the swampland came in. The string theory landscape may be vast, but there may be an even vaster swampland somewhere out there. So the term swampland is used to refer to the space of seemingly consistent quantum field theories that are nonetheless inconsistent when you couple the theory to gravity. So knowing where the boundaries are, we can still try to make predictions, even though the landscape may be vast. So the question is, what physical properties delineate the landscape from the swampland? And perhaps more interesting to a broad audience like this, what are the physical consequences of these conjectures? Now, there have been a lot of research activities on this subject in the past few years, and even if I limit the scope to my own work, there's still a lot to cover, and I will only have time to tell you only a tiny slice of this research program. I would mostly be talking about the weak gravity conjecture, but even so, I would only have time to touch upon some of the more recent papers. I would also like to briefly highlight the idea behind a recent work with Kim and Barker, in which we initiated the program of using strings and more generally branes to probe the consistencies of EFT coupled to gravity. So the other topics that I won't have time to cover would have to be left for a different occasion. So by now, there are various degrees of understanding for different swarmland criteria and how they're connected to each other. They go by the name of the weak gravity conjecture, the distance conjecture, and more recently the density conjecture. The fact that they are connected to each other gives us confidence about their individual validity. This also suggests that if we can understand very well, perhaps prove one of these conjectures, we may be able to find out what is the underlying reason that unify the various different statements about quantum gravity. Now, by definition, these criteria do not follow from effective field theory considerations alone. So why are they necessary for the consistencies of quantum gravitational theories? In a recent work, we argue why certain swarmland criteria are invisible from a point particle point of view, but they show up when you try to probe the theory with extended objects. So the idea is to use the completeness of the spectrum of states to test the consistencies of EFT coupled to gravity. So for example, if your gravitational theory contains a two-form, there are strings-like object that couples to it. Now, the two-form fields transform under local gauge and Lorentz symmetries. As a result, the string action itself is not invariant under these transformations, resulting in an anomaly inflow. So we can now check whether this anomaly inflow can be cancelled by local anomalies in a unitary world-sheet theory. And if this cancellation cannot occur, the theory is inconsistent because strings which exist in this theories pose an anomaly. So we begin by considering some 10 and 6-dimensional theories, gravitational theories, because gauge and gravitational anomalies severely restrict the possibilities. We could use the same approach to constrain 4-dimensional theories, but gauge and gravitational anomalies are not so restricted in 4 dimensions, and there are fewer clear targets. So we illustrate the power of this approach with only a few examples and with only strings as probes. But we expect this program of using brains to probe the consistencies of the theory when you couple them to gravity has much wider applicabilities. In fact, coming back to the 10-dimensional anomaly theories that we talked about before, we show that the two 10-dimensional anomaly theories with funny gauge groups, E8 times U1 to the 248 and U1 to the 496, that have so far not been realized in any string constructions are indeed inconsistent because there are anomaly inflows that cannot be cancelled by unitary world-sheet theory. There are two forms in these theories, and that means they are strings. But when you look at the local anomalies of the strings, they cannot cancel the anomaly inflow from above. So moving on to 6 dimensions, there are known infinite family of anomaly-free supergravity theories. They are typically characterized by an unbounded rank for the gauge group, or an unbounded number of tensor multiplets, or metafields and exotic representations. And we show that unitarity of current algebra of the worldsheet, the string probes, can rule out some of these infinite families. Now, this is the basic idea, and I would have to refer you to our paper for more details. So having established that there is a swarmland, and it's in 10 dimensions and in 6 dimensions, let us revisit some of the conjectures of quantum gravity. There are many of them. The most well-known is perhaps the statement that there are no global symmetries in quantum gravity. And again, there are many ways to motivate this conjecture. For example, you can motivate this from black hole physics. Because of the no-hair theorem, the Hawking radiation of a black hole is insensitive to the global charge it carries. So one could imagine throwing matter with global charge into the black hole. As these black holes with different global charge Hawking radiated mass, you end up having infinitely many indistinguishable states within the same mass range, within a finite mass range. And this is thermodynamically problematic. It doesn't satisfy the entropy bound, for instance. So, indeed, in string theory, as far as we know, all symmetries are gauged. So there was a proof of these statements within the framework of perturbative string theory back in the 80s. And this conjecture has recently been revisited in light of the CFT. So there have been quite a lot of evidence that all the symmetries we find in string theory are either gauged or they have to be broken. This conjecture has many technological applications. For example, it can be used to show that if the dark matter sector carries a tiny electric charge, there's necessarily a new massless gauge boson. And the argument is basically that if the dark sector carries a charge that is not quantized with respect to E, the electric charge, you can construct neutral operators purely with the standard model fields or purely with the dark matter fields. And as a result, there's a global symmetry that acts only on the dark sector, which, as we argue, cannot exist unless the theory is gauged. So then what is the weak gravity conjecture? So the weak gravity conjecture can be thought of as an upgrade of the previous statements that I made. Since global symmetries can be thought of as gauge symmetries with a vanishingly small gauge coupling, it's natural to suspect that problems would arise if the coupling is weak. The question is how weak the coupling needs to be when you start to see problems, and what problems do you see? So the weak gravity conjecture formalizes this suspicion by postulating that gravity is the weakest force. Of course, this is a scale-dependent statement. The strength of gravity grows as a power law in the ultraviolet, whereas the strength of gauge interactions only runs logarithmically. So at high enough energies, the gravitational force always dominates. But as you will see, the weak gravity conjecture comes with a UV cutoff built in, so this kind of situation does not arise. So the weak gravity conjecture is really a statement about the spectrum of charge states. It requires that for every long-range force, there must exist a state whose charge to mass ratio is bigger than 1 in Planck units, or more precisely the charge to mass ratio of an extremal black hole. So this conjecture in particular implies that extremal black holes can decay unless the black hole is protected by a symmetry, as in the case of a NCTS black hole. Now this is sometimes known as the mild form of weak gravity conjecture, as we only require the existence of some states satisfying this inequality, without any additional condition on what that state might be. So if you apply the weak gravity bound to not electrically charged objects, but rather to magnetically charged objects, you come to the conclusion that there is a UV cutoff that is parametrically weaker than the Planck scale. You can make this argument as follows. The mass of any magnetic object, particular magnetic monopole-like objects, would go inversely with the coupling, and the same with the magnetic charge because of Dirac quantization. And because the scale, the UV cutoff scale, would appear in the mass of this magnetic object, to find that the scale at which the UV cutoff of the theory would be parametrically weaker than the Planck scale. Okay. So in string theory, we could also recognize what that scale is. This is nothing but a string scale, which signals the breakdown of ordinary EFT with only a finite few contacts before gravity becomes strong. So because of this UV cutoff, gravity remains the weakest force.
So the decay you're mentioning is happening by some non-perturbative tunneling, because there will be Hawking radiation, right?
There will be Hawking radiation, but for extremal black hole, it doesn't Hawking radiate, so
yeah.
you will have to emit a charged particle.
By some non-perturbative tunneling?
So at the moment, we are just asking kinematically whether it is possible. So it could be non-perturbative tunneling. So kinematically, you need to have an object that carries that charge for the decay to be possible. Okay, so now the weak gravity conjecture was put forth more than 10 years ago, but there has been a resurgence of interest, and it is due largely to its implications in cosmology. So before we turn to evidence for the weak gravity conjecture, let us take a small digression and discuss one of its cosmological implications, namely in constraining inflation. Okay. Now, in addition to density perturbations, inflation also generates gravitational waves, although whether we can detect them depends on the scale of inflation. There is an ongoing global experimental effort looking for primordial gravitational waves imprinted on the CME B mode. And the reason for this interest is that the detection at the targeted level can potentially give us a glimpse of quantum gravity. And the reason is that in the context of single field inflation, the amplitude of gravitational wave is tied to the infraton view range. So if the BMO is at a level that is detectable, namely at the order of 10 to the minus 2 for this number R, or perhaps 10 to the minus 3, you would have concluded that the field range during inflation is super Planckian. Now, without any symmetry protected by Planck scale physics, the infraton potential can receive infinitely many higher order corrections suppressed by the cutoff scales. When you integrate out the heavy degrees of freedom that couple to the infraton, they will generate for you these high dimensional operators suppressed by the cutoff. And if the field range is super pumpkin, these higher order corrections are not under control. And so you would have to rethink about what exactly is the potential over the whole range of the infraton field. And for this reason, axions, or more generally axion-like fields, have been a popular infraton candidate. So I would refer to axion-like fields as any scalar field that has perturbative shift symmetry, even though the field may have nothing to do with QCD. So this is not necessarily the QCD axion. And in string theory, there are many of such axion-like fields. They originate from some higher form gauge symmetries. So when you reduce these higher form gauge symmetries on the internal space, they give rise to scalars with shift symmetries. The shift symmetry descends from the gauge symmetries of the high-dimensional theory. Now, the weak gravity conjecture, as I explained, was formulated in terms of muons and charged particles. So what does that have to do with axion, or more generally axion-like fields? To see how, we can consider a simple example. Let's consider a gauge field in 5 dimensions and compactify the theory to 4 dimensions. So the fifth component of the gauge field now becomes a scalar in 4 dimensions whose shift symmetries originates from the gauge symmetry of the 5-dimensional theory. Now this symmetry is only perturbatively exact, and it is expected to be broken by non-perturbative effects, in particular instantons. So instantons are topologically non-trivial configurations and can be thought of as the world line of the charged particles that go around the compact resonance. So through this picture, you could now relate the instanton action, which controls the suppression of the non-perturbatively generated potential, and the axion decay constant, which defines the axion periodicity in terms of the mass and the charge of the particles in the 5D picture, like this. So if you impose the weak gravity conjecture in 5 dimensions, this would give you a corresponding conditions for the 4-dimensional theory. It now becomes a correlated constraint on the instanton actions, which controls the non-perturbative suppression and the axion decay constant that limits the field range. And even though the argument I gave here is for an axion that originates from a 5D gauge field, this result actually holds more generally, as we have shown in this paper. So this weak gravity bound for axions turn out has interesting implications for cosmology. So in principle, there are infinitely many higher order instanton contributions to the axion potentials. They are hard to compute individually, and not to mention summing them up. So typically, only the leading instanton term is kept. It doesn't mean that the higher instanton term should be absent. For example, this is assumed to be the case in one of the most famous axion inflation models known as natural inflation. So if you look at the instanton generated potential, you find that this potential is flat enough for inflation if the field range, denoted by this, in this picture here, is super Planckian in value. And you could justify dropping the higher instanton terms if the instanton action, which controls the suppression, is sufficiently large. However, the weak gravity conjecture suggests that these conditions cannot be simultaneously satisfied. When you make the field range super Planckian, the instanton action will become small in 5 minutes, and hence this higher order instanton corrections would have to be taken into account. So not anything goes. So this is the end of the little digression. Having seen one of its cosmological implications, let us return to present some evidence for the weak gravity conjecture. And I should say that there are several independent lines of arguments giving support to this conjecture. Arguments that use infrared consistencies like unitarity, causality, black hole thermodynamics, holography, and there was also some very interesting connection with cosmic censorship. So it turns out, if you look at some of the gravity gauge field systems, there are naked singularities, and this naked singularity can be avoided if you have a charged particle satisfying exactly the weak gravity bound. The pair productions of this charged particle would get rid of the singularity. So I will try to highlight some of these ideas. So let's start with the mild form of the weak gravity conjecture. So as we have seen, the mild form of the weak gravity conjecture requires only some states for an extreme of black hole to decay to. We don't know how it decays, but there is kinematically a channel for the black hole to decay if there exists a state satisfying that inequality. So the most natural question one could ask is, could the smaller extremal black hole be such a state? Could a big extremal black hole decay to a smaller one or something else? The notion of extremality is subject to all kinds of corrections, loop corrections and higher derivative corrections. In particular, higher derivative corrections to Einstein-Maxwell theory can correct the black hole solutions and the extremal conditions. Now, these higher derivative corrections are suppressed by the mass of the black hole. So for very large black holes, these high derivative corrections are unimportant, but not so for smaller black holes. And these types of higher derivative corrections have been shown to make some four-dimensional black holes in string theory lighter than the classical extremal bound, meaning that if you were to plot the extremal black hole on QM plot, this is the classical results along the straight line Q equals to M. The higher derivative corrections changes, in some of these cases that have been studied, changes the curve to bend towards this side and not the other way around. Okay. However, other than showing this to be the case in some examples, there was no reasons that have been given to why the curve has to bend this way. So in a recent work, we show that this behavior follows from unitarity and causality, at least for a wide class of theories that can be realized in string theory. So to what extent does our proof apply? Well, we would assume that the UV completion is weakly coupled. That means that if we were to denote the scale, lambda QFT as the scale beyond which the ordinary QFT description breaks down, this scale in string theory would correspond to the string scale, above which we have infinitely many higher spin states. And even so, at the scale when QFT breaks down, the theory is still weakly coupled. This is the case for perturbative string theory. So now, within the assumption that the UV completion is weakly coupled, we find that smaller extremal black holes can satisfy the weak gravity bound, at least in two classes of theories. The first class of theories are theories with light neutral scalars, or particles with spin 2 or above. So light here means lighter than the QFT when QFT description breaks down. So in string theory, this light scalars could be the dilaton or some other moduli that are stabilized below the string scale. Even if there are no light states in the spectrum, our proof still applies when the photon and the graviton are accompanied by different towers of higher spin states, as in theories of open strings. Okay. So since we are considering the decay of a very large black hole, we can go to the deep infrared, where the effective theory describing the dynamics of the black hole consists only of the photon and the graviton. So in 4 dimensions, there are 8 leading high derivative operators one can write down as corrections to the Einstein-Maxwell Lagrange shape. And using the equation of motion, we could recast these 8 operators into 3. One goes like f to the 4th, and the other goes like f dual square, and the other involves the wild tensor. So these higher derivative corrections modify the black hole solutions so the extremal conditions is changed, and proving the mild form of the weak gravity conjecture therefore amounts to proving an inequality for displacement coefficients. So we will now show that this bound with a strict inequality follows from unitarity and causality. So the proof itself is a bit technical, but let me just briefly sketch the argument. The proof consists of 2 steps. First, we show that for the 2 classes of theories that we considered, causality implies a hierarchy in the Wilson coefficients. One of the Wilson coefficients is much smaller than the other 2. And the reason is the high derivative operators involving the wild tensor leads to causality violation. And it has been argued that an infinite tower of higher spin states, just like string theory, is needed to UV complete the theory. And a way to see how causality is violated by the FFW coupling is to consider a photon propagating in a gravitational shockwave background. So in addition to the time delay in general relativity, the FFW coupling leads to a helicity-dependent phase shift. One of the helicity mode experiences a time advancement rather than a time delay. And For here, B is the impact parameter. So for sufficiently small impact parameter or equivalently sufficiently high energy, the the phase enhancement dominates. Now, if the theory contains only particles with spin 2 or below, this causality violation cannot be pure. That's because the phase shift from a particle with spin J goes as to the J minus 1. S is one of the van der Waals parameter. Okay. So, in fact, a finite number of higher spin particles could not cure this causality violation either. However, when you sum over an infinite power of higher spin states, you tend to get a much softer UV behavior, as can be seen, for example, the Reggie behavior of the string scattering amplitude. So this causality violation implies that the ordinary QFT description with only a finite number of states, a finite number of hues, breaks down above a scale that is set by this Wilson coefficient that I call alpha 3. So if the theory contains some like neutral scalars, it would give the scalars would give a dominant contributions to two of the Wilson coefficients, but not to the coefficients that violate causality. So hence we have the asserted hierarchy. But even if there are no such like scalars, if there are different towers of higher spin states, one repeating the photon and the other repeating the graviton, there is similarly a hierarchy, and that is because the open string coupling is parametrically stronger than the closed string coupling. And two of the Wilson coefficients can receive contributions from the open string tower, whereas the coupling that violate causality only receives contributions from the tower associated with the graviton. So that's step one. The second step is to show that positivity of the f to the fourth term follows from unitarity by considering the forward limit of photon scattering. Okay. So in the two classes of theories that we consider, the scattering amplitude satisfies the Poisson bound, and so it is strictly bounded by s squared. So the amplitude can only receive a term that goes like s squared from the higher derivative operators, in particular the operators involving f to the fourth term. So unitarity therefore implies positivity of the Wilson coefficient alpha 1. And combining these results with the previous results that alpha 3 is parametrically small, we obtain the inequality that we want to show. The weak gravity state can be a smaller extremal black hole. Now, having shown that the weak gravity conjecture can be satisfied by some state is a good start. But the mild form of the weak gravity conjecture itself seems rather toothless. The power of the weak gravity conjecture lies on its constraint on low energy physics. In particular, we have seen that the zero form version of the weak gravity conjecture constrains axion inflation. However, if the mild form of the weak gravity conjecture is satisfied by a very massive state corresponding to a very large instanton action, that state gives the negligible contributions to the infraton potential. And so the mild form of the weak gravity conjecture alone cannot rule out axion inflation. There could just be some spectator instantons that are there to satisfy the inequality, but they give no contributions whatsoever to the infraton potential, so you will not be able to tell whether they are there or not. Now, so far all the arguments that we have been given do not rely strongly on what kind of UV completion we have. It should apply to any quantum theory of gravity, but with additional input from string theory, we seem to find evidence that stronger versions of the weak gravity conjecture that involve infinitely many super extremal states should hold in theories that can be embedded into string theory. So, so the question is, could the underlying structure of string theory allow us to infer from the existence of some super extremal black hole the existence of an infinite tower of super extremal states, in particular some states that are in the low-lying spectrum of string theory? In general, we cannot do that. We cannot prove any of such statements. But in the recent work, we show that for extremal black holes with a near-horizon AES-3 geometry, we can use modular invariance, which is intrinsic to string theory, as well as anomaly matching to show that there is a tower of super extremal states interpolated between what you would call protective string states and black holes. So in summary, the Swarmland program aims to identify which quantum field theory can be UV complete when coupled to gravity. And different Swarmland criteria have been used to constrain the physics of inflation, the physics of dark matter, dark energy, and neutrinos. I only have time to tell you only a small subset of these conjectures and their applications. So much remains to be done to fully understand the origin and also the consequences of this conjecture. So I'll stop here. Thank you for your attention.
We have time for maybe just one question.
It's a general question, but if you refer to seemingly consistent quantum theory that can be coupled on quantum gravity, are you particularly having in mind string theory or general consistent quantum theory in general?
So we are doing it in both ways. We try to use as minimum assumption as we could about quantum gravity. In particular, for black hole physics, there's some general law that should apply to other approaches to quantum gravity. And we start from there and see how far we can prove certain statements. And when we cannot go further, we will have to supplement from some of the ideas that are very specific to string theory, like modular invariance is one example. And for instance, in the recent work of Kukui and Harlow, they use holography. So you could argue whether holography is a general property outside string theory or not, but assuming that this is very specific to string, then you could use to show stronger statements. So this seems to be the results that we find. If we make very minimal assumptions about the UV completion, we can prove something. And we can strengthen the statements to, say, infinite number of super extreme states if you add in features of string theory.
Just a quick one.
Yeah.
So I mean, in the black hole decay discussion. So basically, what is saturating the weak gravity bound is the perturbed black hole solution, the smaller black hole.
Yeah.
And that already satisfies it.
Yeah.
So if we just stick with that kind of weak gravity, so that the small black hole satisfy weak gravity conjecture, does that still imply anything about, like, for example, for the coupling constant, the decay constant for the axion?
Yeah, so this is what I alluded to as the mild form. So the mild form, if you can only show the mild form, is still rather weak statement. So one could imagine, in addition to the instanton that generated infraton potential for you, there's a spectator whose only purpose is to satisfy the weak gravity conjecture. So this would be analogous to having a very large black hole satisfying the conjecture. These are black holes with masses much bigger than the Planck scale. So usually we don't include them in the low energy description. And if you have such a state, it could satisfy the weak gravity conjecture and contribute nothing to the infraton potential. So I would say that just the mild form, say, having found a black hole that satisfies the weak gravity conjecture is not enough. But the part of the recent development is to try to push further to see whether you can prove an infinite power version of that conjecture.
Okay, next back, Thank you.